All right, ready to rock and roll. Thank you for coming. I know there's a lot of choice. There's so many things going on. But I hope this will be useful. So let's go. Who am I, and why am I here for? So I manage the cloud platform team at Netflix. And really, what I'm going to talk about is I've contributed to many OSS components. You might have heard of Netflix OSS. It's pretty popular out there. But really, the main thing is, though, that I've been through so many production outages. And that's really what the learnings that we learned from all of these production outages is what we put back into our software, and we've open sourced it so that we could share it with the community. You might think, yeah, big deal, what happens if Netflix goes down, right? That's what I thought. But man, you just have to look at the Twitter feed. You will be so upset because you're at a restaurant just trying to have dinner in peace, but your kids are not going to let you because Netflix is down. So that creates an argument, and it leads to divorce, and too many bad things happen. So really, Netflix has to be up and running all the time. And for it to be up and running all the time with high availability at the scale at which we are running, we got to have a good architecture, right? So I'll talk about the evolution of where we started, where we are at now, and there's a big roadmap, which I'll cover as well. So here's the agenda. We'll talk about Netflix, its background, and its evolution. And monolithic apps, what do they really mean, right? What are the characteristics of a monolithic app? Then why did we embrace microservices? What are these? So we'll go through some of those. And believe me, there are challenges in a microservices architecture, especially when you have to run it at the scale at which we do. And then the backbone of a microservices architecture is really the interprocess communication. The communication that you have to do between each of these target services. We've open sourced a bunch of libraries. Again, what's new, right? So I'll talk a bit about that. And then finally, if we got time, hopefully, we'll do some takeaways and question and answers. How does that sound? Good? All right, let's go. Netflix evolution. Before we go, it's about scale. If there was no scale, life is very easy, right? It's very easy. I think a lot of people already know this, but it's better repeating. At peak, in the United States, 1/3 of all internet traffic is Netflix, right? So we've got upwards of 50 million subscribers. We handle about 2 billion API requests on our edge service per day. In fact, we are such a big microservices shop that we've got more than 500 microservices. For what you see as Netflix.com is essentially powered by hundreds and hundreds of microservices. And I got more than 30-odd engineering teams. Not odd engineering teams, but 30-odd engineering teams. So evolution. About 2008, I'm going to say we were in our own data center. Ages ago, right? I mean, everybody's on the public cloud these days, but back in the days, we had our own private data center. And the architecture that we had at the time is what I call as a monolithic architecture. Anybody can recognize what this building is? It's Burj Al Dubai, so it's in Dubai. And that's the way to scale a monolithic application. You kind of keep building on top and top and top. It's like a vertically scaled service, right? And circa 2010 is when we embraced the public cloud, Amazon, in fact. And I think we were one of the very first, or one of the first 10 or so big internet scale companies to embrace AWS. And we took that as an opportunity to go to service-oriented architecture. And that's the evolution that I'll take you through in the rest of the talk. So monolithic app. What are the characteristics of a monolithic app? The way I look at it, I kind of tend to think in terms of pictures. A monolithic app is like a train with many cars on it, right? Or wagons, if you prefer. From an architectural point of view, this is what it would look like. Essentially, at Netflix, we support about 1,000 device types. Device types are things like Xbox, PS3, your browsers, DVD players, what have you, right? And they come through, so it all were deployed on one single monolithic application. Every code that you could think of was in that one single WAR file, for those familiar with the Tomcat deployment, which was backed, again, by one single Oracle database, right? That was the monolithic architecture we embraced. Nothing bad about it. At the scale which we were at in 2008, that was the perfectly right thing to do, all right? And if you are there now, perhaps it is the right thing to do for you. So so the pros of that architecture for us was that it's got good IDE support. You could just fire up your Eclipse, your IntelliJ, and your whole entire code base is right there. Very easy to look at all the APIs, life is good. All your calls are essentially in-memory calls. So really, it's computationally fast, good. It's pretty easy to scale out horizontally, because essentially you just got one application. You just have to clone it however many times you need, and you're good to go. And you really need just one central operations team, right? So these are all good things. A pretty happy customer. And if that's where you're at, good. Nothing wrong with that, right? But as the organization grows, as you hire a lot more people, it's natural that teams will be formed, right? And as time progresses, what happens is that your code base literally grows like that. That's when things start getting interesting, right? So an evolution of a monolithic application, what happens is that you will hire from many different other companies. And if you were a Java shop, this person would go, well, I used to use R, I used to use Python in my previous company, why not? I mean, that's the right thing to use. So it becomes difficult for all of these folks to contribute to that one single code base, which perhaps is in Java or whatever other languages that you use. The other thing that tends to happen is that these components over a period of time get entangled in each other, as described in this diagram, right? Has that happened to you? Has happened to us. Gradually, over a period of time, everything naturally gravitates in this way. You form small teams, and these teams, for all intents and purposes, will have their own characteristics, as described by this particular train analogy here, right? And the other thing that happens is, as you grow your code base and as the number of teams increases, your deployment cycle will really go bigger. Because of a large code base, the amount of things that you have to test, even if you touch one tiny code, is a lot, right? And we have 15, 20, 30 teams. They all move at their own pace. And really, people will be like, no, I'm not ready yet. You got to wait. So typically, a monolithic application tends to have days, if not weeks, of deployment cycles. These are all characteristics. In terms of scaling, I said it was easy to scale, because essentially it's just a single copy, and you just have to clone it any number of times. However, please do note that it's difficult to scale it in an undifferentiated manner. In other words, if your product catalog component is more popular and is taking a lot of requests, you cannot scale that differently from your customer service component, right? So that's the aspect of scaling. When it comes to availability, that's when things start getting really interesting. So at this point, I'd like to tell you a story. What happened back in 2008? This is a story where I say that a single missing semicolon brought down the whole Netflix.com site for hours. All it was missing was a single semicolon. So the story is that we stored our movie reviews in Oracle. And at the time, we had to display this in various devices where HTML was not the first-class citizen, like PS3 or Xbox or something. So this enterprising developer thought of coming up with his own syntax in order to format bold and italics, the movie reviews content. And for some reason, he chose semicolon as the parser delimiter to determine this. Some other enterprising developer used a tool that did not have a semicolon in it. So if you're familiar with the Tomcat architecture, which has like a pre-configured limit of 200 threads, a request would land up on the thread, and the thread would try to go load the movie review data, cannot find a semicolon, would keep going on an infinite loop. Very soon, in seconds, really, all your 200 Tomcat threads are dead in the water, right? So the whole site went down. So really, a single missing semicolon brought down the whole site for hours together. I kind of liken it to this picture here. So if you really think about it, even if one of the wagons or your cars of a train go down, you kind of have to halt the entire train. You simply cannot proceed. And that's when you really, really start thinking. So what's the tipping point? The tipping point to me, before you move to a microservices-like architecture, is if you got an organizational growth, essentially with multiple teams, and each of these teams would have diverse functionalities and features and characteristics and behavior and personality, and you reach a bottleneck in your deployment architecture where you go, okay, I'm done with this. I really need better availability. That's perhaps the time you should start thinking of microservices. How many people here actually use microservices? Oh, a lot. That is good. That is good. So let's talk about microservices. One of the main challenges, really, of what are microservices, kind of overheard in a previous conference. So hipster SOA. I like the definition. That's a good one. But before we, what's the difference between an SOA and a microservices? Is it just old wine in a new bottle? Let's define it in the following way. Let's define what is not a microservice. And I've been asked this question many number of times. What do you mean by microservice? Could it have like 100 Python lines? Is that a microservice? If I go beyond 100 Python lines, is that not a microservice anymore? Microservices are not defined, at least in my book, in terms of team size, how many developers are contributing to it, how many lines of code it has, or how many number of APIs or endpoint that it publishes. A heavier service doesn't automatically become a mega service, and a lighter one doesn't become a microservice. So that's what it's not about. To me, what it is about, and I kind of paraphrase perhaps Adrian Cockcroft, Martin Fowler, and others, microservices are about many, many, many smaller, lightweight services that adhere to the single responsibility principle, which is do one thing, just one thing, but do it right. And they are independently managed. In other words, if in the previous train diagram, there's an engineer perhaps in the engine and he's driving the whole train. In the microservices, each individual team responsible for a small service should manage it independently. And that leads us to the DevOps model, right? It's another buzzword going on. I'm going to drop quite a few buzzwords in the talk as we go. So it, again, goes back to the good old Unix philosophy, which is write programs that do one thing and do it well, and make them such that they can work together to do a better good. I don't know of any Unix command or program that could print out all the misspelled words in a document. However, you can string together a set of small Unix commands and can come up with that big, nice program that gives you misspelled words in a document, right? So think about microservices in a similar manner. And if you go back to the train analogy, it kind of goes like this. Yes, you can still do the same thing in a monolithic application, but notice that they are tightly coupled to each other. That's the key word, tightly coupled, as opposed to a microservices architecture, which we go away from the train model, we go to the cars model, in which every single service is specialized. There are some services that have characteristics of going pretty fast, others are pickup trucks, and others are wagon, whatever, right? So each with a different purpose. Again, revisiting the old model of monolithic applications, everything is baked into a single application, right? In a microservices architecture, the same application will be split up into multiple services, each with its own responsibility, right? So this is one of the architectural patterns, which is you got a load balancer, ELBs perhaps, and then you got an API gateway. At Netflix, we call it the edge gateway or the API gateway, and which is backed by a lot of hundreds and hundreds of microservices, right? Another characteristics of microservice is that each of these services tend to have their own databases. Remember the previous one was just one Oracle database. In the next one, each service is backed by its own database. So we defined what is a microservice, but why? Why would we want to go to a microservices architecture? It's because it gives you faster and simpler deployment and rollbacks. Each individual team can follow its own path, its own timeline in order to deploy your services. If a particular service is better written in Python, you got that opportunity. If it's better written in Java, well, so be it. So it gives you the right of language to choose the right tool for the right service. It does buy you greater resiliency, as in fault isolation. If one of your microservices goes down, it's okay. Your whole site is not down, just that one functionality is down. Hence, it gives you better availability, only if architected right. I'll explain how, all right? But before I proceed, let's put this picture in our mind, capture it in our mind, the concept of service dependency graph. Okay? Service dependency graph is for every call path that your API gateway handles, it perhaps depends on n number of target services, right? Dependency services, which in turn depend on other services. So this particular thing is a definition of a service dependency graph. So with that concept in mind, let's now go through challenges. So now you're on board. Now you want to use microservices. What really are the challenges of microservices? And believe me, there are many, many, many. We could have an entire conference just on microservices challenges, yeah? All right, but the good news is these have solutions. These have solutions, so don't fear, we'll walk through some of them, all right? So let's go through them. What are the challenges? Again, going back to that picture, monolithic versus microservices architecture. Instead of building vertically, you kind of go into a suburban sprawl, right? Multiple small buildings spread across. What it really means is that when you give this freedom to your teams, when you build individualized cars, unless you define the rules of the road, traffic book or your DMV booklet, you're going to land up in chaos. I can guarantee you that, all right? How? Let's go through some of those issues. Polyglot ecosystem. One of the pros of a microservices architecture is that it allows you, as a service owner, to develop in Java, Python, Node.js, R, whichever one, right? So you're talking multiple languages here. However, that creates a problem as far as operational homogeneity goes, because each of these have different frameworks, and it becomes very difficult from an operational point of view to understand what's going on in the overall ecosystem, right? So what do we do? The concept that we came up with is this concept of sidecars. Essentially, at Netflix, we open source Prana. Diptanu here open source Prana last week. And what it is the concept is pretty simple. It's OK for your main application to be written in Java, Python, R, Node.js, what have you. However, to keep operational homogeneity, you could deploy Prana alongside as a sidecar or as an agent, if you will, that provides all the platform services to your ecosystem. What are platform services? Things like configuration management, service discovery, metrics, those sort of things, right? So sidecar is your friend if you embrace a microservices architecture. Another challenge is service discovery. When you got one monolithic application, there's just you. There's nobody else to talk to. It's all good. It's all fine. Even if you have 2, 3, 4, 5, 10 services, it's OK. You can still name them. I've got 2 kids, and it's not too difficult to remember their names, right? However, when you embrace a microservices architecture, you've now got hundreds and hundreds of services, and more keep propping up every day in a big organization like ours. How do you even keep track of who's who, right? That's where service discovery becomes important. So at Netflix, we again, this is a theme. We open source everything we do. So we open source Eureka, which is a service discovery software. What it does is essentially says that every time an instance comes up, it says, hey, I'm an instance. I'm coming up on behalf of, actually, I'm an account service instance using AMI X version Y, coming up on port 8007, yada, yada, yada. These are metadata associated with that instance. And it registers itself with a single registry called Eureka, right? And that helps other services to discover all the others, the rest of the ecosystem. So that's Eureka. That's your friend. So if you embrace microservices architecture, you would need some sort of a discovery or mechanism. We use Eureka. There are other choices, Console, and a few others come to mind. OK, so that was the challenge of service discovery. Moving on, chattiness and fan out. What do I mean by that? When you have a single monolithic application, the one user request that lands up on your application is really the only request. But when you have microservices, one single request that lands up on your API gateway fans out into many, many, many requests to your microservices. So that creates chattiness. In the case of Netflix, like I said, we handle about 2 billion requests per day. Well, that goes into 20 billion, 25 billion other requests in the internal ecosystem. Right? That's a lot of different calls out to what's the solution? Solution is perhaps to use server caching. So instead of putting load on your target services, why not cache that data? So first make a call to a distributed caching system like memcached, right? And much faster, reduces the load on your target service. That's one pattern. Another pattern would be a little bit more advanced. What you can do is you can capture the results from each of these services, kind of like a composed or a materialized view, if you will, and then store that in your memcached copy, right? Again, reduces the load on your target dependency services by a lot. Moving forward, bottlenecks and hotspots. What are they? Imagine, again, remember I said we need to keep the service dependency graph in our mind. This is one service dependency graph in which app, service X, Y, and Z, they all depend on user account service. Okay? So what happens in this scenario is that every single request that goes to the application translates into 4 requests to the user account service. So essentially, that creates a bottleneck. That creates a hotspot for that particular service. Right? What's the solution? Well, one of the solutions is to simply capture the very first application that makes a request into user account service could just simply keep that data and pass that data around as HTTP headers, right? So now there are 2 good things that happen. A, you will reduce the load on user account service. B, you will reduce the dependencies, and that's a very good thing to do in microservices. Try your best to depend on as few dependency services as possible. All right? Now the challenge, payload serialization. So typically what happens in a microservices architecture, you kind of daisy chain your requests, right? Service A depends on service B, which needs to call service C, which blah, 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 right? So what happens there is that the overall response time increases. And it especially increases and creates problems if you use different serialization mechanism. Yeah? So if you use Avro, another service responds back in XML, another one tries to do JSON, now you have to pay the overhead of actually deserializing it and serializing it, deserializing it, serializing it. So that's a tough choice. So one of the ideas is to just embrace a single serialization format. Because these are microservices in the backend, nobody needs to care about a JSON or an XML API. Choose one and go with it. It reduces your overall serialization overhead. Dependency management. We talked a lot about dependencies, right? Target dependencies. It's a challenge to manage the dependencies. What do I mean by that? In a microservices architecture, your application, the one on the top, depends on many, many target dependency services. In this diagram, A, B, C, all the way to R. Remember earlier in the talk, I said one single semicolon brought down all of Netflix site? You would think embracing microservices architecture would make us much more available and better. Not true. Not true. How? Because even if you got one rogue dependency service, in this case, dependency I, the same thing can happen, which is your user request threads can block and go latent on talking to that one dependency service. And pretty soon, all of your threads are occupied just talking to that one dependency service. So you're host. What's the solution? Again, what's the theme? We've open sourced yet another library called Hystrix. So if you are familiar with distributed systems concept like circuit breakers, retries, bulkheading, fallback, that's what Hystrix provides you with. So what's the concept? It's pretty simple. So what we do is we take all of these calls to the dependency services and create thread pools specific to that dependency service. So in this particular case, 5 threads are allocated to talk to dependency I. So if dependency I goes south, it's OK. It's only 5 threads, right? So the rest of your ecosystem, rest of your threads are doing just fine. So Hystrix is your friend when it comes to guarding yourself from your dependency services. Scaling dependencies, another challenge. What happens is that let's assume you got 100 requests per second coming into your application, right? What if the load changes and now you've got 200 requests per second? You have to scale your particular application, of course. What about your services? What about your target services? They need to be scaled up as well, right? So what we do at Netflix is we use AWS autoscaling. And that's your friend. Why? Because if you configure AWS ASGs with RPS or with CPU load average, as and when the load on your particular target service increases, it's going to autoscale itself, right? So now you've got a well-orchestrated system which allows you to scale up and down as your load increases or decreases. For those that are sufficiently advanced, we've blogged about predictive autoscaling, right? It's different from reactive autoscaling. Predictive, especially if your company has got very high scale and it follows a certain pattern. In the case of Netflix, evenings are peak time, right? Daytime is not as much. Weekends are peak time, right? So there's a trend. And Scryer, and we blogged about it, what it does is it predicts what the scale is going to be 5 minutes from now and scale up the instances accordingly. So go look up Scryer on the tech blog. Load balancers. Interesting topic, right? When you have a microservices architecture, you got choices. You can have ELBs, perhaps, fronting each of your microservices. But the challenge is, since you got hundreds of microservices, you will really need to configure hundreds of corresponding ELBs, right? That's one thing. So that's just the way to create ELBs. And what we've done at Netflix is we've put the smarts of load balancing on the client side. So we have this open source library for IPC called Ribbon, which I'm going to talk about. And it's got a built-in smart load balancer, which load balances requests across each of these microservices. And it's specially well-tuned for AWS. What it does is it looks at statistics in terms of the requests that have been outstanding to each of these instances in the cloud, zone A, zone B, zone C, and it employs statistical inference to know which zones to avoid, which instances to avoid. And so you get the benefits of doing a client-side load balancer via the open source library called Ribbon. So to summarize on the load balancer, the best practice is to use the ELBs on your public edge API gateways. And for your internal mid-tier or backend microservices, you can employ client-side load balancing. All right? Service dependency visualization. That's another challenge. Why is that a challenge? If you're anything like Netflix, you got hundreds and hundreds of microservices. It's kind of like, where is Waldo, right? Where are you in the picture? Way over there. If you are a developer, you would want to answer the following questions. How many dependencies does my service have? What's the call volume? Are there any dependency services running hot? Remember the user account hotspot that I talked about? So these are questions you need to answer. And the first thing you really need to do is to have a good service dependency visualization tool. Else, you'll be like the cat trying to unravel the threads in the ball. So what we've done at Netflix is we've invested in a service visualization tool, and we call it SALP. And it gives you a much simplified view of your service dependency graph. In this particular example, there's an edge service talking to a gateway, and you can hover on the edge between the nodes, and you can find out what is the call volume, how many requests are going through, what's the average latency, what's the median, what's the 99th percentile latency. These are good tools to have. This is a small demo of an actual Netflix dependency graph. The service names have been anonymized. And what you can do is you can hover over the edge, one of those dark blue things over there. When you click on them, you will get the call volume between these two nodes, so on and so forth. Another thing that happens in a microservices architecture is which service caused the failure. When things go south, in a monolithic application, there's only one application, but in a microservices, any of these hundreds of microservices could have been the culprit. Typically, it's going to be a blaming game. Now, ask him, I don't know, maybe it's him. Maybe it's his service, right? So really what you need to do is it becomes difficult to grep through hundreds and hundreds of machines with logs. What you need is a distributed grep sort of a system. Or you can use a log event pipeline, and you could use AWS Kinesis, or we've open sourced another system. Again, this is the internal Netflix distributed grep system called Biopsys. It's capable of doing a grep on all of your log files across thousands of AWS instances. That's one way to do it. Another way is via Netflix Sudo. So you essentially pipe all of your log events through this single pipeline, and then use Hadoop or any of the other real-time analysis tools to understand where the problem is in a microservice. So where are we? We talked about a few challenges. We talked some of the solutions. So what are the best practices? Let's go through some of the best practices. One best practice is to isolate each of your microservices. And AWS Security Group is your friend. When you own a microservice, you want to make sure that you will not get DOSed, right, by your own infrastructure. You need to guard yourself from who can talk to your particular service. So use the AWS security groups as one way to do that. That's one best practice. Another one is test your resiliency. That is the definite good best practice. I'm going to quote Ben Franklin here. He said, there are only two things certain in life, death and taxes. I'm going to add to that and say there are actually three things certain in life, death, taxes, and outages in production. Guaranteed, right? So what you need to do is test the resiliency of your services. Test them for latency, test them for errors, test them for what happens if an entire dependency service goes away. Earlier today, there was a talk, and Josh and Naresh, colleagues of mine, talked about fit. So the concept there is, what happens if a particular service is not available? In this case, let's assume that the three services lined up in red are not available. What does that mean for your ecosystem? It's an important question to answer. So fit is the talk that Naresh and Josh gave earlier today. How many people attended that? Awesome. For those that did not, again, the videos and the presentation will be available, so I highly recommend to go through that content. Simian Army. Anybody here has not heard of Netflix Chaos Monkey? All right, so pretty much everyone knows about it. So again, employ Simian Army to make sure that your microservices architecture can withstand all sorts of failures and be highly available. All right? Good dependency management tool or deployment management tool. Anybody heard of Netflix Asgard? All right, so Asgard is the open source tool we use in order to do deployment and management. And it's got really a lot of good concepts built into it. Concepts like canary, red-black pushes. These are all your friend when you deploy a microservices-based architecture. Yeah? So now we talked about, so far we talked about some best practices. Earlier I mentioned that inter-process communication is the backbone of a microservices architecture. So let's go a little bit deeper into inter-process communication. So at Netflix, inter-process communication is a pretty meaty area. And if you look at this thing, on the left-hand side you will see ribbon, and you'll see a few components there. I'll talk about them. On this right-hand side you'll see server, right? Inter-process communication is nothing but communication between a client and a server. As we discussed earlier, Eureka is the service registry, and Ribbon, the client, consults Eureka to get a list of instances that it can talk to if it wants to target a particular server. And it employs its load balancer in order to pick the right service to talk to. And all the resilient features that we talked about, caching, remember caching? That's provided by EV Cache. Remember the circuit breaker, the fault tolerance logic, all of that is provided by Hystrix. So that really is a simplified picture, if you will, of our inter-process communication. And we employ Apache HTTP client, which does mostly REST calls between client and server. We are happy with this architecture, but there's one thing that we wanted to improve, and that's throughput. When you embrace microservices architecture, remember there's going to be a fan out, right? You have to talk to n number of dependency services. If you talk to these services in a serial fashion, you're going to increase your overall response time. It's better to make these calls in an asynchronous manner, perhaps as a batch call, right? For anybody that's done asynchronous programming, if you know about Java futures and what they call as callback hell, right? That's a difficult load to bear. So what we've done is we came up with this new stack called IPC 2.0 stack. And essentially, instead of going with the blocking architecture, we've gone completely reactive. So instead of Apache HTTP client, we now built another open source offering called as RxNetty on top of the popular Netty library. And it allows us to do reactive extension pattern. So what does it mean in reality? What it really means is that we now give you more options than just HTTP. You could do UDP, WebSockets, SSE, any of these, right? So it's a completely reactive architecture. So when you're doing microservices, asynchronous, batch operations are your friend, and reactive architecture is a fantastic architecture to go through. So why is this important? It's important from a performance or throughput point of view. Because when you have a threaded, in one of the variations that I show over here, the Tomcat threaded model has got a certain characteristics in terms of the number of requests that it can process, essentially the throughput of the system. It's been shown by many benchmarks that if you embrace an event loop-based system, such as Node.js or Netty, you can almost double the throughput. And that's a good thing. Why is that a good thing? Because that allows you to reduce your EC2 footprint by quite a bit, right? More money in your pocket. And so reactive extensions are your friend. So if you look at Ribbon 2.0 or Karyon 2.0, these embrace the reactive extensions pattern, and it's good for your microservices architecture. So here's an example of a code of how it looks like. It's pretty simple. Pretty simple. All you're doing here is defining a service called as a movie service. And remember, we talked about caching. We talked about Hystrix. So it's all annotation-based. All you're saying is that I need to talk to that REST URI there called user ID recommendations. And in case that call does not go through, use the fallback handler that I annotated there. And oh, by the way, before you make that call, please verify that it's not in the cache. If it's in the cache, I would prefer to get it from the cache, right? Everything that we talked about in the previous slides. All of that can be accomplished with just a few annotations and 3 or 4 lines of code. Pretty simple, right? So Netflix OSS, as we've talked about, we've open sourced quite a few of these libraries and frameworks. And you can leverage them too. You can leverage them too. It's all on GitHub. A few that we went through today was Eureka for service registry, Karyon for as a server container, Ribbon for IPC client, Hystrix, Archaeus, Servo. There's about 40 or 48. I can't even keep track anymore, quite a few. Anybody attended Ruslan's talk on Netflix OSS and Docker? OK, if you haven't attended that talk, it was just an hour ago. I highly recommend that you catch the video or presentation later on. It shows how you can, within 10 minutes is all it'll take for you to take all of these and put it on your laptop and give it a run. That's it. All right? So please go take a look at that talk. So there are quite a few other talks here at reInvent. Again, I highly recommend that you follow through and see what they have to offer. Takeaways. Finally, what are we here for? So the takeaways are monolithic applications are good. Nothing wrong with them. If your organization is in a place in which that's the right architecture for you, good to go. However, microservices architecture has its own pros and benefits. There are challenges as well, right? It's not easy. There are challenges. The good news is that these challenges have got easy solutions, right? And quite a few of these solutions are open sourced, especially by Netflix, and you can just embrace them. The other important thing is that we have to be thankful to AWS as the public cloud offering, because quite a few of these things are very difficult to achieve in a private data center. Things like provisioning, on-demand provisioning, things like auto-scaling, security groups, whatever, right? Any number of components that's been out there makes it much more easier to embrace microservices compared to doing it in your own data center without these features. So that's really the takeaway. And there's a lot of information out there in these links. techblog.netflix.com has got a lot of articles on the various architectural principles that we talked about. All the open source software is available on netflix.github.io. Again, if you are particularly interested in microservices, I recommend going through Martin Fowler's website. There's quite a few. And we've got a Netflix booth downstairs, and please come talk to us. I know this talk talked about a lot of different points, and we're out there hanging out just to answer questions. So we're not there to sell Netflix service, right? I believe you're all using it already, so we're there to talk tech. We're there to talk tech. We'll be more than happy to talk tech. I know I'm between you and the pub crawl. And if you are doing the pub crawl as well, I would love to chat with you. Diptanu, any of your colleagues, we're kind of wearing the same kind of shirt today. Come grab us, and more than happy to answer your questions. So in the last few minutes that we've got, we can take some questions. Any questions? Yes, sir. Thank you. Thank you.